It is a fundamental postulate of physics that the laws of nature be expressed by equations that are valid for all coordinate systems or reference frames. Alternatively, we say that the laws of nature are covariant, which means that they have the same form in all coordinate systems. A systematic method of investigating the behavior of quantities that undergo a coordinate transformation is the subject matter of tensor analysis. In developing the mathematical subject of absolute differential geometry, Gauss, Riemann, and Christoffel introduced the concept of a tensor. The subject of absolute tensor calculus, or tensor analysis, was introduced and developed by Ricci Curbastro and his student Levi Civita. And Einstein made extensive use of the tensor calculus in his formulation of the general theory of relativity. Today, we're going to be talking about tensor algebra. Often, the solutions of a physical problem can be made easier by first selecting an appropriate coordinate system. In general, it is easier to solve problems involving spherical geometry by use of spherical coordinates than by use of Cartesian coordinates. Therefore, it is important to develop the system for making the transformation from Cartesian coordinates to other coordinate systems. And that brings us to general curvilinear coordinates. Let the position of a point P in space be completely described by P U1, U2, U3, where U1, U2, and U3 are three single-valued functions of position. For U1 equaling a constant, U2 equaling a constant, and U3 equaling a constant, the U's are three surfaces which intersect at the point P. And these surfaces are called coordinate surfaces. And the three curves of intersection are called coordinate lines. Now we can transform between two coordinate systems in the U old coordinates and the X new coordinates, giving a function that will map between them. Tangents to the coordinate lines at point P are called coordinate axes, and if the relative orientation of the coordinate surfaces change from point to point, the UI coordinates are called general curvilinear coordinates. If the three surfaces are everywhere mutually perpendicular, the UI coordinates are called orthogonal curvilinear coordinates. The position vector of the point P is a function of the UI coordinates. That is, we may write the vector r in terms of the UI coordinates. Then we can define an element of displacement, dr, given by the partial derivative dr du times the differential du with respect to the directions 1, 2, and 3. And thus we can write this as a sum. The square length then is the dot product of these two differentials. And therefore we have two summations to consider over the ui and the uj coordinates. Now the dr dui coordinates are tangent to the curves ui, respectively. So what this means is that the tangents are restricted to the curvilinear surfaces. Since dr du1 implies that u2 and u3 are fixed, r of u1 is then therefore constrained to move along the u1 curve on the u1 surface. Now if we define a set of coordinate axes given by the dr du coordinates, then normalizing this axis vector gives us the normal or the unit basis vectors. And therefore the ds squared can be calculated using the metric tensor gij, and the line element gij times dui and duj gives us this metric. In an orthonormal system, the axis vectors ai, aj are dotted to equal 0 when I and j are not equal, and dotted to equal 1 when I is equal to j. And since the metric gij is only valid for when I and j are equal to each other, we get this element of line. And therefore we may write ds1 is the square root of g11 times du1, ds2 and ds3 accordingly. Now, we can relabel these as h1 du1, h2 du2, and h3 du3, where the hi's are just simply scale factors. And so those scale factors correct for the curvilinear surfaces and the curvilinear curves in our coordinate system. If one considers a Cartesian system, where all the metrics are equal to 1, then the line element can be just written in this way. And writing these things out as a sum with their partial differential units, we get a sense of seeing where this comes from as we expand it out. So the metric tensor here, given as a summation of these curvilinear basis vectors, allows us to define elements of area as well as elements of volume in the curvilinear system. And since we're on the note of volume elements, it's notable to mention here that the following volume element is calculated in the following way. Using a dot and a cross product, which gives us this element of volume. But if we reimagine what is going on here and redefine back what we had as the h1, h2, and h3, We see this here as the determinant, which is popularly known as the Jacobian of the transformation. Transformations of coordinates in linear spaces. Consider a set of mutually independent variables. x1, x2, x3 up to sub n, or rather super n, are the coordinates of a point. And the collection of all such points constitutes an n-dimensional linear space. We'll denote this as the space Vn. Now, the set of n equations, which is a mapping from one coordinate system to the other, is a new set of coordinates, a barred set of coordinates. So transformations between these two coordinate systems is what we want to look at. So now, let's differentiate this particular function mapping with respect to the coordinate xj. The x bar system, differentiated with respect to the xj system, is found by the summation of the differential summed over the coordinate j. That differential phi may be rewritten in terms of the barred coordinate system. And using the Einstein convention, we can just drop the summation, where it is assumed or understood that summation is happening over the j index. So therefore, if we let the vector x in the unbarred system be given by x super I in Vn, then x bar super I is given by the function phi of I. And the differential can be defined in this way, using the Jacobian. The Jacobian is equal to 0 in this transformation, therefore making it invertible. Tensors and their transformations. Let's talk about some of the characteristics of tensors. Well, first, what is a tensor? One can say it is a collection of indices, which includes subscripts and superscripts. Superscripts are known as contravariant indices, whereas the subscripts down below are known as the covariant indices. And tensors can have a mix of both upper and lower indices, making it a mixed tensor. And thus, because of those indices, we can assign a rank to a tensor and discuss its components. The rank or order of a tensor is the number of indices which are not being summed over in an expression. So some of the types of tensors we'll see. One, we could have a rank 0 tensor, which is just a scalar tensor. Then we could have a rank 1 tensor in contravariant form here, or a rank 1 tensor in covariant form here. A rank 2 covariant tensor is written here, and a mixed tensor might look as follows. And this would be considered a rank 3 tensor because of the fact that we would be summing over the indice I, and in that index I we'll talk about why that summation happens. In an n-dimensional space, the number of components of a tensor of rank r is n to the r power. So now we're going to develop a little bit of algebra for the tensors. Now our first rank tensor is probably the most familiar. It is a vector. And so the first rank tensor is a set of components A super j. And they transform according to the following equation, changing it into a barred system. And thus we can transform a contravariant in one system to a contravariant in another system, a contravariant of rank 1. And this is how we represent vectors. And if we want to solve this equation for the contravariant in the unbarred system, we'll multiply both sides of that equation by dxk d bar I. And that's going to give us something that will produce a Kronecker delta, and thus giving us the form that we're looking for. So we can transform back and forth in between two tensors of rank 1, or two vectors in one coordinate system and another. Now, if we write down b sub k as the components of a covariant tensor of rank 1, also known as a covector, then this product will be invariant in both systems. In other words, it'll produce a scalar. And they obey the following transformation laws. Pause the video now if you need to look at these indices and the barred systems a little closer. But then we can produce this equation, which then produces this transformation rule for the covariant tensor of rank 1. As we proceed, you'll see and you'll notice we'll make some certain changes of indices so that we can match components together. If you like this video, please hit that like, subscribe, and notification bell for more videos. Now, some of the higher ranking tensors, probably ones that you won't encounter too much. Let's say if we have, well, there are certain ones as they get bigger, perhaps the rank 2 tensors you will encounter, but higher than that, maybe if you're doing differential geometry with the Riemann tensor, and we'll talk about that in the next video. So a second order ranked tensor can transform as follows, and you'll begin to notice a pattern amongst the higher ranking tensors. So here I'm giving examples of the contravariant, the covariant, and the mixed tensor transformations for rank 2 tensors. So let's really consider if we had some abstract number of indices here. And we'll use a mixed tensor to make this point. If we follow how many indices there are, you'll see how many partial derivative transformation products are needed in this expression. And so working with higher ranking tensors is really about mastering the work with their indices. And that brings up one point here. If you swap a set of indices and you get an equivalent tensor, we say the tensor is symmetric. But if you swap a set of indices and you get the negative of that tensor, we say it is an anti-symmetric tensor. And that has some very significant meaning in the world of vectors. So this brings us to a discussion on polar and axial vectors. So first, vectors whose components are completely specified by the following transformation rule that we developed earlier. Okay, those vectors are called polar vectors, or proper vectors. And examples of these vectors would be like a displacement vector, or ones describing mechanical force. In contrast, what is an axial vector? Well, in Cartesian coordinates, it is possible to obtain a vector t from the cross product of two polar vectors, calling them a and b. And so a cross b gives us the vector t, which in component form reads as follows. And thus we get an anti-symmetric tensor. Tensors such as these are known as axial vectors, or pseudovectors. Angular velocity would be an example of an axial vector. So now on to some tensor algebra. And of course we'll start with the discussion on addition, and of course subtraction moves along with this. You can only add or subtract two tensors of the same rank. And this might seem familiar, as a tensor can also be thought of as a kind of matrix. So two tensors of identical ranks can be added together to give you a new tensor of the same identical rank. Now when it comes to multiplication, we have to be more specific, and here we'll talk about outer product. So given two mixed tensors with their given indices, the outer product is going to be a new tensor that incorporates all of their indices together in one, thus increasing the rank of that given tensor. Now, an operation that we must consider is one called contraction, where we reduce the number of indices by summing over a particular index. So if we look at this expression here, we're summing over the index I because it shows up in both the top and the bottom in the contra and the covariant positions, and thus the summation is understood, and therefore contraction occurs. And therefore a new tensor is written in its place. The inner product, a different type of multiplication, is the combination of outer multiplication plus a contraction. So for instance, if we had a mixed tensor here that was the product of a tensor a and b, you can see that the upper in b is the letter k, and the lower index in a is k. That's the summation index, and that's going to create a contraction of the index. Thus, we only retain the indices that have not been summed over. The quotient law. It's a simple indirect test to see if a set of quantities qualifies or forms the components of a tensor. And it does this by looking at how quantities transform. Do they transform properly under the transformation rules for tensors? So let's say we consider an inner product where CPK is the product of two tensors, one that is thought to be a tensor and one that is just an arbitrary tensor. So we'll let A be the tensor that we're testing, and B be an arbitrary tensor that we're using to test it. So the quotient law states that if the tensor A, the quantities in it, form a component of a contravariant tensor, if B happens to be an arbitrary tensor, and you also get that C is a tensor, then you have confirmed, using the quotient law, that A is a tensor. Again, you're using B to test A, and you're seeing if you get C, which is also qualifying as a tensor. And we check the relations through their transformation laws that we developed earlier. And this gives us a chance to really practice how to write out these partial derivative scalar components to our tensors. So carefully making a transformation change of index, letting R go to L, and the indices I and J go to S and T. The reason that we're doing this is we're trying to join both the left and the right-hand side of the equation, and so we must make a change of index in order to join them together. So now we've changed the B tensor with more familiar coefficient indexes on both sides of the equation, so that when we bring them to one side of the equation, we can then solve for parts of this equation. That is, we can set the coefficients here equal to 0, and multiplying both sides by dx super a d sub bar p and summing over p, we can then find a relation which is basically the test for the quotient law of tensors. Because what we were doing is we're testing that tensor A to make sure it transforms properly under the transformation of tensors rule. And so since we can extract this expression from that equation, we can see that the tensor does in fact transform properly. This is how we use the quotient law. Next, for an arbitrary tensor with components a sub v, we may form the inner product with the Kronecker delta to exchange indices. And we'll check here to make sure that the Kronecker delta transforms under the proper tensor rule. And so a little rearranging of our indices here, we find that the Kronecker delta does in fact pass the quotient law test. Now if one considers again the line element, ds squared equal to gij x super I dx super j in the Riemann space. For a Euclidean space, the metric is the Kronecker delta, and therefore the expression simplifies to this. The natural sum that is everyone is used to from calculus class. Now, it is required that this line element be independent of the coordinate system, as it is expressible through tensor notation. We check the transformation rules. Since in one coordinate system it must be equal or equivalent in the other coordinate system, we then transform the rules accordingly, bring everything to one side of the equation, and see what we get as a result to see if the metric tensor does in fact transform under the proper rules that tensor transformations follow. So now we isolate the term that we need, and thus we require and get that the metric tensor in the barred system transforms appropriately to the unbarred system. The quotient law is satisfied. Another important tensor is known as the tensor associate to some arbitrary tensor. So let's say we have an arbitrary tensor A super J, and the tensor associate is the result of taking this tensor and its inner product with the metric tensor. This will create a new covariant form of the contravariant vector that we started with. And the purpose of the tensor associate is to raise, or in this case lower, an index. And one can show that this particular equation transforms properly. Thus, the tensor associate becomes an indispensable tool in not only tensor algebra, but also in tensor calculus. Now again, in Cartesian coordinates, we have the metric tensor as the Kronecker delta. And thus, if we want to transform by raising the index, we're going to make use of, well, it is sometimes referred to as the reciprocal associate tensor, but it's also referred to as the inverse metric tensor. And it is the cofactor transpose divided by the determinant of the metric tensor. And thus, multiplying the metric with its inverse yields the Kronecker delta. And that allows us to raise and lower indices with tensors. So now we have, in summary, done a lot of things to establish the algebra of tensors. We've talked about curvilinear coordinates and how they transform between coordinate systems. We've discussed what a tensor is, the notation, rank, and indices, and a little bit about how tensor algebra works. The types of multiplication, polar and axial vectors, the quotient law for testing vectors and tensors, associate tensors for lowering and raising indices. And next time, we are now geared up to talk about tensor calculus. For now, thank you for joining me, friends. And remember, hit that like, subscribe, and notification bell for more videos. And stay tuned for the next one. Thanks for watching.